All right, welcome Kim 151 to chapter 20.4. We're a little ahead of schedule, so that's awesome for us. We just have 4 slides to get through today, and then we're finished with chapter 20. All right, so the focus of this chapter is all about free energy, which you know as delta G, equilibrium, and reaction direction. And so how are we going to determine reaction direction of a specific reaction, and if a reaction is at equilibrium or if it's going to go to the left spontaneously or to the right spontaneously? And the way that we do that is by comparing Q and K. So remember that K is the equilibrium constant at a particular temperature, and it means that the reaction is at equilibrium. Q is the reaction quotient, and it refers to the ratio of product and reactants at any one point of the reaction. Q can equal K, it can be greater than K, or it can be smaller than K. So I want you to remember the QK number line. On the left-hand side, we see a little q, and when our q, or when the ratio of products to reactants is smaller than the given equilibrium constant, that means the reaction is spontaneous in the forward or in the right direction, going to the right. If q is larger than k, that means the reaction is spontaneous to the left. Now there's a third option where you can see the 3 outlined options. The third one is if Q is equal to K, and we know that means the reaction is at equilibrium, and we know from the previous section that that means that the reaction is not spontaneous in either direction. So what's the meaning of comparing Q and K? Well, Q and K, comparing the two, gives us an idea, again, of which direction the reaction will go. So if Q is less than K, that means the ratio between Q and K is less than 1. If Q is greater than K, that means the ratio between Q and K is greater than 1. And if Q is equal to K, that means the ratio between the two is equal to 1. So we're going to use that to determine what the free energy of a reaction is. So seen below in image 8, the free energy and its relation to reaction progress formula is seen. Delta G, which is free energy, is equal to RT, R being the universal R constant, 8.314 joules per mole Kelvin, times the temperature that the reaction is taking place, times the natural log of Q over K, which is the same thing as RT natural log of Q minus RT natural log of K. So Q again represents the quotient or the ratio of products to reactants, and K represents the ratio of products to reactants at equilibrium. All right, oftentimes we'll see a delta G or delta H or delta S with a little degree sign next to it in the upper right-hand corner, and that stands for standard state. That means the reaction that you are calculating for occurs at standard state. What does standard state mean? Can be seen in the table near the top of the page. If the phase is a solid, that means the solid is pure. If the phase is liquid, that means the liquid is pure. If it is a solution, that means it is at 1 molar concentration. And if it is a gas, that means it is at 1 atmosphere pressure. So plugging all those values in for Q, regardless of the reaction, would render Q to be equal to 1. So at standard state, Q is equal to 1. So we get the following equation when we're calculating delta G at standard state. So if we take the equation on the bottom of the last page and plug in 1 for Q, the natural log of 1 is equal to 0, making this entire expression equal to 0, giving us this new equation for free energy at standard state. So let's look at our first example question. Calculate K for the following reaction at 298 K. We have carbon monoxide gas plus 1/2 O2 makes carbon dioxide. So in order to approach this problem, I've uploaded 2 pictures from your Appendix B in the back of your book. And you can use these to identify the thermodynamic values you need to complete this problem. So a little hint if you want to try this on your own and then just fast forward to see the answer, you will be using the equation above. You'll first need to solve for your delta G naught, and then you'll plug that in to the equation above to solve for your K. So if you'd like to try that on your own, go ahead and pause the video, solve it, and then resume when you're finished. All right, so the first thing we did was solve for delta G of reaction, plugged in the values from the thermodynamic tables up above. Notice CO2 and CO are on the left-hand side, and oxygen is on the right-hand side with a value of 0. So I plugged those in. Products come first, then reactants, keeping into consideration the coefficients. I got a negative 256.8 kilojoule per mole answer. I used delta G naught equation that we have just up above in image 9, solve for K by itself. I have to E both sides to cancel out the natural log. So I end up with K is equal to E to the negative delta G naught over RT. Remember that your delta G value is a negative already, so the 2 negatives cancel, and that this R value is 8.314 joules per mole Kelvin. Because your delta G value above is in kilojoules per mole, one of the units needs to be converted so that those 2 units can cancel to give you a unitless answer for K. Okay, so we have example question 2 on this page and then example question 3, and then we are done with chapter 20, new material. In the following lectures, we'll do a lot of different types of practice problems because we've really only scratched the surface here in terms of the type of questions that can be asked. Okay, so looking at example question 2, it says use the equilibrium constant given to calculate delta G naught for the following reaction at 298 K. So we have sulfur plus sulfur dioxide plus oxygen gives sulfur trioxide, and that's a K value of 7.0 times 10 to the 24. So very similar to our previous question, our previous problem, we're using that delta G naught equation in image 9. Instead of solving for K in this, and like the previous scenario, we're now solving for delta G naught, which is a little bit simpler. So go ahead and attempt that using image 9's equation. Pause the video and then come back to see the answer. All right, so using my delta G naught equation from the previous page, I have delta G naught is equal to negative RT natural log of K. I'm going to plug in all my values. So delta G naught is equal to negative 8.314 joules per mole times Kelvin times 298 K. This is given in the problem. This right here is a constant times the natural log of 7.0 times 10 to the 24. Plugging that into my calculator, I will get negative 141,736.821 joules per mole. Delta G naught values, delta G values in general are generally given in kilojoules per mole, so that would mean this is equal to negative 141.736821 kilojoules per mole. And then taking into consideration significant figures, 7.0 has 2 sig figs, the fewest sig figs of all. So that means my answer is negative 1.4 times 10 squared kilojoules per mole, and that is your final answer. All right, last but not least is example question 3. I'm going to blow this up a little. These molecular scenes represent 3 mixtures in which A2 and B2 are forming AB. Each molecule represents 0.10 atmosphere. The equation is A2 plus B2 equals 2AB, and your delta G naught is negative 3.4 kilojoules per mole. So you are tasked with solving A and B. If mixture 1 is at equilibrium, calculate K, and B, which mixture has the most negative delta G and which has the most positive. So again, pause, attempt the problem, come back to see the solution. And then if you have any questions, ask them during lecture, or you could ask them during office hours. So pause the video here to try the problem on your own. All right, so your answer to A would be 4. I plugged in the number of molecules for the product times the pressure that it gave to us in the question. It said that each molecule corresponded to 0.10 atmospheres. And then I squared it because of the 2 in the coefficient in the balanced reaction. I divided it by the pressures for the reactants. It gave me a K of 4. Now I'm going to compare reaction 2 diagram and reaction 3 diagram by calculating their Q's and comparing those to the K that I got in letter A. So let's scroll down and see how I did that. I just wrote a reminder, delta G naught is equal to negative RT ln K, and that gives me a value of negative 3.4 kilojoules per mole. So that tells you essentially that at standard state, when all components are at 1 atmosphere, the reaction is spontaneous in the forward direction or to the right. Okay, the reaction going to the right. Because it's not yet at K, it's not yet at equilibrium. Since 1 stands for or represents equilibrium, that means this is the first diagram is not spontaneous in any direction because it's reached equilibrium. So its delta G value is 0. So I just have to consider reaction diagram 2 and 3. All right, so remember that a positive delta G value means the reaction is spontaneous to the left. That means your Q is greater than K, so it needs to go back toward K to reach equilibrium. And then a negative delta G means the reaction is spontaneous to the right, so we're looking for a Q value that's smaller than K. So plugging in all the values that I have for reaction 2 and 3, I took these from the diagrams and took into consideration the number of molecules for products and reactants. For reaction 2, I get 0.44, and for reaction 3, I get 36. This number is smaller than my K value, which is 4, so that means the reaction is spontaneous to the right. It has to go toward the right to reach K, and that means it has a negative delta G. And the opposite is true for reaction 3. I have 36 for reaction 3's Q, so that means the reaction has to go to the left in the reverse direction in order to reach equilibrium, so the reaction delta G is positive. So the most negative would be reaction 2, the most positive is reaction 3, and reaction 1 is 0 because it's at equilibrium. Let me know if you have any questions, and that's the end of chapter 20 content.